So here, right?
Scroll down.
Oh, okay.
Scroll down and hit agree. That will give you the internet.
Oh, all right. Okay, let me see. Let me go to the first one. Let me go back. I was working hard the last minute. What do I do?
Well, I was just saying for this one.
Oh,
Connect the internet.
okay, that's a good idea. Hold on a second, because otherwise it wouldn't show me the response time. Agree?
Agree. I don't know if that'll help your slide.
Yeah, well, it might. It's kind of slow. I'm done here? Okay.
So welcome back this afternoon.
Maybe 1 minute.
From IBM. I've known him for something like 30 years. He was a postdoc in our group back. He's one of the earliest people to get into active mapping.
Anzaga, you should remember that. Of course, your statistical mechanics. I'm not going to show any Feynman then. Okay, great. Thank you, Peter. Yeah, so it's a pleasure to be here. I mean, I heard about the summer school a lot, but I have not been here. I just don't remember what it's so hot. You remember? Anyway, so these two gentlemen, I like to really thank. I mean, Yang, of course, my longtime collaborator and sort of the co-conspirator for this whole thing. You may or may not know, but he's actually playing a very important role in the flocking. Because I remember after we did the flocking model with John, in 2000, I went spent a month in Saclay and working with Yu. I think that was the start of the European flocking. I mean, he really played it. I mean, he's just so good. And a lot of the stuff that I talk about, experimental stuff, and he was heavily involved. I'm not. So I actually borrowed a lot of charts. I saw him last 2 weeks ago in Aspen, so I asked the chart after that. But of course, all the main papers I wrote was with John Toner, University of Oregon. Okay, anyway, without further ado, so I'll tell you a little bit about the two parts about flocking or active matter. One is hydrodynamics, which is very ancient stuff, right? So which we did in the late 90s with John. So this is more, the first part is more historical. I hope you give you a mindset where we were when we started this and where we ended with and why is that important? Maybe. The second part is something new. So has to do with what I have been doing after flocking is I changed to one of the fields I was interested in was biology, right? So cellular molecular biology. And there, I think the common theme is that it's all very highly non-equilibrium system. As such that even in the steady state, in the non-equilibrium, highly non-equilibrium system, even in the steady state, it costs a lot of energy to maintain that steady state. So we take that point of view, and that energy cost in maintain that non-equilibrium steady state is crucial for the function of those biological systems that we study, including adaptation, synchronization of clocks, so on and so forth. So recently we have taken that thought, that line of thought, and applied it to flocking. Saying, okay, how much energy does it cost to flock? Okay, so that's the last part of my talk, I wish I can get to. That's new, something that we're actively doing. So hopefully you can get something out of it, but it's actually not already published. Okay. This is a 3-part lecture. So I usually talk very, very fast, so stop me. stop because this is I don't have enough material if I talk that fast to cover the whole 90 minutes for one lecture and 3 lectures. So please do that. Okay. All right. So this is about active matter. When we worked on flocking, there was not such a term of active matter. So I went back to the authority here, Wikipedia. I try to find out what exactly is active matter, right? So you can read, I can read, and let me just read it to you because it's actually important. Active matter is matter. Of course, it's a matter. It's something of substance composed of large number of active agents. So it's talking about large number. So there go thermodynamic limit or hydrodynamic limit becomes relevant. Agent, so individual particle agent, what they call, each of which consumes energy. So there's energy where it comes in. It wasn't originally in the whole active matter or flocking theory, but later on, the third part of my third lecture, I'll get into that. In order to move is very important, or exert chemical force. Such systems are intrinsically out of thermal equilibrium, intrinsically, because it actually has to move. Unlike thermal system, we relax towards equilibrium and system that with boundary condition imposing static current. In this case, you can imagine a turbulent, a large container of water. We shake it from the boundary, and energy can cascading down. Active matter system break time reversal symmetry. Even the green part is what I wrote. Even in statistical steady state. So even just seemingly doing nothing. So if you measure something, it actually doesn't change with time. Right, probability of being in a particular state doesn't change with time. Even in that case, there's underlying current, probability current keep flowing through, and that actually costs you energy to maintain. Okay, most examples are biological in origin and span all fields of living, from bacteria and self-organizing biopolymer to schools of fish and flocks of birds. So the motivation I will show you next was actually started, of course, schools of fish and flocks of birds. Right? But I will tell you more recent work is actually on bacteria and self-organizing biopolymer. However, a great deal of current experimental work is going to the system, the artificial system, which I will also touch upon a little bit. Active matter is a relatively new material classification in soft matter. I'm not sure about that. Yeah, okay, so active matter, I think, is a little bit more than just being soft. It's actually being active and purposeful and injection of energy and so on. So the most extensive study model, like Vicsek model, so we'll talk about Vicsek model, which is the canonical model, dated from 1995. The last paragraph, before I move on, is research in active matter combine analytical technique, numeric simulation, and experiment. And notable analytical approach include, this is not my word, okay, this is on Wikipedia, except for the blue part, the green part. No, almost, no. So including hydrodynamics, which I will talk about, this is sort of the subject of the summer school, kinetic theory and non-equilibrium statistical physics, that's the last lecture. Yes. Oh. Walking, bird sound, connection there. Yeah, there's a chirping sound, right?
Is there a video?
I don't think so. You think it might be my computer? Interesting. Oh man, that is spooky. What do you want to do? You want to close out here? Unplug it and plug it in again? I have no idea. So let's try another board. So does it, but there's no. I don't think I have any, I know any computer games anyway. That's a good idea. What do you?
Is there a way to?
Of course. Of course, easy said than done. There should be something coming up. Yeah, try this one. Oh, I have no. Already turn it off. That's the first time it happened. I guess if you use the backflow, there's one of those. What do you want to do? I think I did that. Okay, this setting.
Sorry about that.
Yeah. Okay, let's see. Anybody knows about this? Okay. Let's see, where is my, there's a song. Good? All right. Unexpected. Did you do that? Well, it's not quite there.
Huh.
Don't jinx. All right, so let me give you a little bit of outline of what.
You're okay?
Okay, so let me give you a bit of outline what this 3 lectures about. The first lecture is introduction. So I'm going to show you some fun movies and fun historical facts and anecdotes. I'll end with the linear analysis of the hydrodynamic equation, which give you the sort of the conundrum, right? How could it ever have long-range order in 2 dimensions? And lecture 2, this is probably pretty heavy. I don't know how much I'm going to go into that. I'll show you the breakdown of the linear hydrodynamics in dimension less than 4. And just the idea. I'm not going to go into the full RG theory, right? Just the idea of what RG can do and what's the basic idea of RG in the context of this problem. And I'll do a little bit of analysis to show you the result and end with the breakdown of the Mermin-Wigner theorem for flocking problem. And if I have more time, I'll tell you more about the mode, the hydrodynamic mode, the fluctuation mode, sound mode in the system. Right. Okay. And the third lecture, as I advertised, will be something new about energetics of flocking. I'll demonstrate the detail balance, the breakdown of detail balance in a simpler lattice model of flocking. And then from there, I'll tell you about how do you actually compute cost of maintaining a non-equilibrium steady state, in this case, flocking state, and energy cost of flocking in this particular simple model called AIM, right? Which I will tell you a little bit about in the first lecture already, and energy performance trade-off in flocking. Okay, so that's something that we're actually actively doing. So I'm very eager to actually get to that part. If you can go through this part first, which is also important to set the base. Okay. All right. So everybody must have seen this video, right? Multiple times. You have fish school. So basically, collecting motion of agents, in the words of the Wikipedia, are ubiquitous in nature, and fascinated people, why and how, right? Mostly how. The school of fish, there's no obvious leader in this school that tells everybody to go the same direction. In the same goes flock, and seems to be keeping the coherent structure, and also grazing wildebeest, which makes a very nice picture. Hundreds of thousands of them can graze in the Serengeti. So So you can easily find videos. This is very popular. The reason you know it's popular because when I search for movies for flocking, they always point me to YouTube. So you only put popular video movies in the YouTube, right? Others like bacteria swarming, you can easily find them in the supplemental material of PNS on Nature. Nobody wants to watch them. Okay, but I will show the second type, right? This you can easily find. Okay, now, so you're of course fascinated as sort of physicists or mathematically oriented people. You like to model it, try to understand how it works, right? So apparently, physicists are not the first group of people that should model flocking behavior. Guess who the first group is? What? Nope. Yeah, that little bit of that. Okay. Computer scientists. So Craig Reynolds, if you look, actually this is a very famous guy, actually. He won an Academy Award in '88 because of his work in animation. So they actually asked a different question. If you want to simulate in animation a large group of behavior, right? A behavior of a large group, well, how are you going to do it? You can prescribe the trajectory for each individual bird. That's going to be at that time, at least memory-wise, something impossible, right? Or you can do the distributed computing part, which is what Craig Reynolds did. Basically, in his abstract, again, I will read it because it's actually very interesting, the historical perspective. The aggregate of, I actually, if you notice the title of his, we actually borrowed the title in our paper, in the PRE paper in 1998. So basically flocks, herds, and schools. So he was talking about how in the computer at that time, how you actually simulate the group behavior, right? You can use the prescribed approach, which is dumb, not very efficient, right? And not very dynamic. I mean, you will prescribe, you can only limit by your imagination of how the flock will behave, right? There's no spontaneous behavior that can arise. So the simulated flock is an elaboration of particle systems. So he already had the idea of agent and particle. By the way, he's the one who actually coined the word boid. So it's between bird and oid. Oid is a name we usually give to particle, right? So boid was invention of Craig Reynolds. The aggregate motion of the simulated flock is created by a distributed behavior model. So the key is distributed. Every individual has his own intelligence, and it uses such intelligence to make a decision. So everybody is based on their own intelligence, and as a result, the whole thing flock together, have collective behavior, right? So he's looking at the problem. He's getting to the heart of the problem, but from a different approach, from different perspective, right? So each simulation bird is implemented as an independent actor that navigates according to a local perception of dynamic environment. Local, right, is the key word. And the law of simulated physics that roots its motion and a set of behavior programmed into it by the animator to choose himself. So you don't have a global leader to prescribe trajectory. You just set a set of rules and hand it to every bird, and they follow the same. Every bird follows the same rule and make decision based on the local environment. And the aggregated motion of simulated flock is the result of a dense interaction of the relatively simple behavior of the individual simulated birds, right? Again, this is a very much along the line of what physicists think, right? The rules are simple. The behaviors can be complex and interesting, and maybe unexpected, right? So this is the Journal of Computer Graphics, '87, and he works in AI, right? So AI is all the rage now. So this guy actually is a pioneer for AI, which is recognized, actually. He was recognized as one of the pioneers of AI. And this is just for fun. He actually worked on the film Tron. I don't know if anybody know about this movie. But definitely people know about this movie, right? Batman Returns. And in '98, he actually was awarded the Academy Award for recognition, pioneering contribution, development of three-dimensional computer animation for motion picture production. So this is a picture from the paper. And I highly recommend you to check out his website. I mean, he was a, pretty advanced, in computer science, because in '87 he's signing his electronic email as his correspondence, and he actually already had a website already back in the late '80s to show how the boys work. Okay. I hope this is fun. I mean, I don't want to go to the old paper and dig out the old formula. Anyway, you can find those. So this you may not find because everybody taught you from the beginning about Vicsek model. Vicsek is not the first one to come up with model. Here's another one. Another group of people, biologists, behavior scientists, and applied mathematicians. So these are guys that applied mathematicians working together with biologists. They actually was trying to understand the motion of a finite group of fish, fish school, how they move. So they actually come up with pretty much the same rule as later on we'll see Vicsek's rule. So what do you have? You have body interaction. So these are the rules, right? Body interaction have 3 radius, R1, R2, and R3, and a little angle at the back. So you're pointing towards north, okay? So there's an angle behind you, of course, you cannot see. So you're not sensing anybody behind you with a certain angle. That's a parameter you can tune. And this R1 is a small radius, which if you get too close, you should, there's a force to push you apart. So there's a force if you imagine that it's repulsive here and pretty much flat here. If you're within R1 and R2, then you're happy. You can keep going where you're going without the body interaction. If between R2 and R3, you should attract because you don't want to fly apart. It's a finite group, right? So this is actually a very clever rule that these people implemented to simulate a school of fish. And then you have alignment. Basically, so this guy, if you want to align to this, you want this angle. If you want to align to this neighbor in the cone that spanned by this shaded area, you see this guy and this guy, this fish and this fish. So you should orient pretty much in the middle, right? Towards the middle, average angle between the two fish within your region of detection. Okay. So they just implement this rule with few parameters, and this is the result that they show in this paper, Journal of Theoretical Biology, of a group of fish, little bit larger group, a little bit smaller group. That they study how it depends on the group size, how it depends on the parameters, how it depends on the noise level, so on and so forth. Right. So I think to me, these are the real pioneers of trying to model the specific behavior of flocking behavior, right, for different purposes. Yes. Yeah, these are just parameters in the model. So for example, you can have a different rule. So for example, if your distance is less than R1, you can have a repulsive interaction which can go like 1 over R, or whatever rule, exponential, e to the minus R over R1, right? And then here, your potential will just be flat because that force will be 0. And here, your force will have, your potential will come up, right? So if you want to draw a potential, then it would look like something like this, right? So you have a repulsive interaction and flat goes up, right? So this is your R1, this is your R2, this is your R3. I don't know what happened here. Here, just out of your sight, you don't see it, right? So basically, if you take a derivative of this potential, you get a force that is repulsive. You have no force, no body force, and you have a force that attracts back to each other. Yeah, fish size. So it's dimensionless by the fish body size. So I guess he drew. I don't know. This is the proportion. I don't know the detail, but here's the paper. And actually, people are going back to this more detailed model these days to understand. So this obviously means something quite interesting. This means that interaction is asymmetric, right? If I'm sitting here, I see you, but you don't see me. asymmetric interaction actually is very interesting because asymmetric interaction means that, again, detail balance is broken, if you wish, or this is an intrinsically non-equilibrium system. But they don't care about that for in this model. They just want to see the behavior-wise, whether it duplicates, it will actually replicate the whatever seen experiment. Actually, people do experiment for fish school, right? Even early days, yes. I think these guys are working with experimentalists. I have a picture to show that, but there was a nice Scientific American a paper on the subject back in the early 90s or late 80s. Okay. Your question? Yes. Yes, not because of that asymmetry, because this symmetry is recovered because everybody is equal in terms of their absolute leadership or not. Because if you're behind, but you may not be always behind. But there may be a symmetry breaking. I don't exclude that. But what people always joke about is that the leader are the mutants that doesn't listen to others. So then automatically become the leader because if I'm just floating around ahead of everybody, and if I see you floating and I move towards you, whereas if you even if you go very far from the flock, you don't average over the direction of other guys. So leaders are stubborn mutants. Anyway, that's a joke, but in the biological example that people worked on these days, like in wound healing, right? So there are cells which can differentiate into what people presumably call the leader cell, which their interaction with others is weaker. Then, so exactly going back to your point is that asymmetry actually plays a role in the sense that the interaction, the propensity of listening to others is much weaker, and the speed that it's moving is faster. So everybody try to catch up with. So there's a hypothesis that they are leader cells within the cells being regenerated after the wound happened. Okay. I think I'm doing very well in slowing down, so I don't mind at all, actually. Okay, so as I said, all the inspiration happened prior to 90s and 2000. We're mostly in the macroscopic world that our eyes can see, right? So this is actually fascinating us. But in fact, flocking behavior also exists in the microscopic world. I'll tell you two classes of example. One is bacteria. Actually, this is something that I worked on a lot, but on individual cell basis, looking at how they move, what they sense, and so on. But in this paper, for example, in 2010, by Hepeng Zhang and in Harry Sweeney's group in Austin, Texas, they basically just take it seriously, this group collective behavior. They actually measure the velocity of individual cell. These are bacteria, E. coli, right? E. coli moves. E. coli moves due to the flagella. You see the flagella behind. This is actually a drawing. This actually flagella come out of across the cell is about 2 microns long, and the diameter is about 1 micron, and it has up to 5 or 10, up to 6 flagella coming out of the cell body, and the flagella can be as long as 10 micron, very long. So they actually can form a coherent bundle behind the cell body if they're rotating, if all the motors, so this is driven by a motor, rotary motor at the base of each flagella, and rotation frequency can be as high as hundreds of hertz, right? If you rotate in the same direction, counterclockwise, all the 4 or 5 or 6 flagella will actually form a bundle, and that bundle will actually drive, like a propeller, will drive the cell moving forward. And the cell can actually move as fast as 20 microns per second, right? This is actually pretty fast. Consider it's actually 2 microns long. So this is like, it's like a, yeah, so it's actually 10 body size per second, right? So it's pretty fast. So it moves, so that satisfies one condition, it moves. And it also aligns. When it collides, it seems to align its direction of motion. So in the high density regime, we actually frequently collide with each other. They actually measure the correlation function of the speed of each individual flagella and its orientation, right? And this is the correlation function. As you see, the pairwise correlation function, forgot what this is, probably positional. Yeah, it seems to doesn't go back to zero, right? So I have long range order, and so is orientation correlation and velocity, the speed correlation itself. So you see, it has some very interesting collective behavior. So what is showing here is actually the red correspond to a particular range of angle. So the red ones are pretty much aligned, basically. And the purple are aligned in different direction. So it's color coded by the angle of the velocity. So you see that they actually bond together, right? So the red ones are together, blue ones are together, and so on. So that's basically showing you that picture. So this has been a favorite system. Bacteria colony, bacteria swarming has been a pretty interesting system to study. In 2017, for example, the Sumino's group has shown that the motion actually can be described by a Vicsek-like model. And this is a 2D wet active pneumatics, meaning that in this case, it's so dense, it's so close, you cannot ignore the fluid, that the cells are embedded in fluid. The fluid motion has to be considered. So this is a difference between dry. When I say, all I'm going to talk about today is dry. Dry means that there's no fluid, no actual fluid motion that you have to consider. This is a wet, because then you form this very large structure. Right? So if you squint your eye, you can see dislocation, disclination, all that good stuff that's going on. And in this system, they actually even see a very weak synchronization. These are two tracer particles you put in the suspension. Yes. It's moving because driven by the bacteria, and as a result, it actually also acts back to the bacteria, right? Oh, this is actually this is actually the fluid motion, I think. I have to check, but you can check this paper. It's a very beautiful paper, illustrated about. I think they have tracer bows for example. This is probably the fluid. This is definitely the fluid. The tracer particle is put in the fluid. So you can also have in this paper. They also have labels for the cells themselves, and you can see the tracer particle is not hopping on individual cell being carried around. It's really driven by the flow itself. Okay. This is actually a very nice study, because when they see the tracer particles seem to synchronize, but if you look at individual cell, they are not synchronized. They're not going this way. They're actually going pretty random. So it's on average, because the fluid is averaging over the sort of a seemingly stochastic motion, but there's some average large-scale motion still persists that drives the tracer particle around. All right, a lot of motivation. Second example, which is actually very popular these days, is called motility assay. On the left, you see is a motor protein called kinesin, right? This motor protein is a biological engine. It's called linear motor, so they walk on a linear track, and in this case, the microtubule. It's a polymer, if you wish. It's a tube that it works on. It has two ends, positive end and negative end, and the motor protein actually works from one end to another end. So it's actually directional, right? So what you see on a normal situation is that the tracks lay down the railroad, right? And this guy is the engine. It carries cargo from one place to another. So it's an active transport process that's powered by these molecular engines in the real biological system. So this system has been used to do active matter in the other way. So basically, if you pin the head of the motor protein here, like here, if you actually on a substrate, you put some glue, you glue this head, so you cannot move. It cannot move, but it can still push the tube, right? And you're just observing the tube. So they flip it, they tether the motor protein, they painted the whole thing by a layer of motor protein, and they stick it there, and you put some ATP. Of course, you have to put energy source. ATP is the source, energy source. You put some ATP in the solution, and you put some microtubule, in this case, some lens, and just watch it. So what you see is the microtubule being moving along, but they have no engine or they have no power. It's being pushed below by these molecular motors. Right? Okay, so that's basically the system you look at. So the second, so this is actually somewhat artificial because that doesn't happen in real biological system, because real biological is that way around, right? The tube is actually fixed, but the motor is moving up and down, carried cargoes to different places. Okay, so people have studied this system a lot, and you can probably, this is actually widely cited paper these days that are mostly about this type of motility assay, right? So for example, in this paper, 2012, the Sumino and all, and you see this is a very thin layer, 2-dimension. So you don't have any crossing, right? The tube cannot cross each other, right? So it's really, if you hit each other, you have either a line, or we'll see later. And what they find is that it actually formed these vortices, right? It's amazing, beautiful. Look at. That is a collective motion. Okay, so actually, in this same paper, they actually did a more careful study of how two microtubules, when they move towards each other, what happens to their orientation, right? And they see that, for example, panel A shows actually complete alignment. So when at t equals 0, they come in with an angle. And after the collision, roughly happened at 0.60 seconds. After they come out of the collision, it's pretty much aligned, right? At 1.33 seconds, they pretty much aligned. And this is a sort of a pneumatic case because it doesn't have any directionality. So anti-parallel, anti-alignment also happens. So just pass through each other like this, right? Either they go like this, or they can go like this, but align. They can also, of course, because it's really high 2-dimension, they cannot really cross each other. So when the angle is large, it's like more 90 degrees. One will actually stop and wait until this guy passes, and this will keep moving. So they actually did statistics on that the red solid line is alignment, this is anti-alignment, and this is other cases. The most cases, when the angle is away from 90 degrees, most cases lead to either alignment or anti-alignment, basically alignment. Yes?
So these systems, because they're active, these pictures that you're drawing look like almost like
yeah. I don't know. I mean, that's a good observation. I don't know whether that's true or not. Right? But when they align, they may not be aligned right in the middle. They can be aligned choosing whatever. There's a dominant one, they just go with the dominant one. But something you can check. But in principle, they should not. Yeah. Okay. And last movie I'm going to show you is actually, this is actually very popular also. We're having fun, right? Is this work by Dodgy Group? That was done with Brandeis. I think it's UCSB now. It's actually very, very interesting because this thing, I really like it because of this. So you see, this is the same material, different behavior, right? The left is just dead. The middle, it moves, kind of moved, a little slow. The right is very high, very, very active. So what's the difference? Again, energy is very, very important, right? So this thing actually burns ATP to maintain it. So this at the left is actually, there's no ATP. Of course, it's dead. just laying there. This one has a little bit 57 micromolar, and this is 1.4 millimolar. So it's almost like 100, 220-fold difference, and the motion shows. Although here you already see structure, but here it moves much faster, much more dynamic. So you're encouraged to look into this system if you're in the soft matter. These are the systems that you actually really need theory and modeling to try to understand the details of how it actually works. Okay, so that's the frontier. Yeah.
So you're seeing some sort of organization as you increase.
Exactly. Yeah, but of course that organization depends on that concentration you put on in the first place. Yeah. So all these sort of interesting dynamics because it's active, right? Okay, so there's three key properties for the individual agent. I call the Boyds, following the Reynolds. So the agent for individual flocking system has to have these three things in common. Well, we sort of have to. They always move, right? They move because there's some internal engine driven by activity of the agent itself, which consumes energy because it's not because they consume energy so that actually they keep moving. And these agents or Boyds are often called self-propelled particles because of that. It's self-propelled. It's propelled by itself. It's not driven by external force. Not just by external force. It has its own internal engine. The alignment is also important. That they have direction of motion. So therefore, the alignment of that motion is actually a very important part of the flocking dynamics, right? And the part about alignment is that the alignment is actually local. If everybody's aligned with everybody globally, then the problem is much less interesting, right? And it's also unachievable. Okay, and the third part is that there's noise in the system, right? It's not a perfect decision making. You actually have noise in the system. So move, align, noise in the system. These are the three things that has to be in the model, right? So here comes the model. So you ask, where, I mean, this is about hydrodynamics of the flocking. So where does it come from, right? I did not work on hydrodynamics flocking when I left Caltech, right? 94, summer of 94, I joined IBM. August, I still remember, August 1st, 1994, I left Caltech and I joined. At Caltech, I was working on pattern formation, Rayleigh Bernard convection, rotating Rayleigh Bernard convection. I think there was somebody talking about that today, right? So we were working on instability, called Cooper's Law's instability, that we worked on as an example of spatial temporal chaos. But anyway, that aside, I was interested in dynamics. I was interested in non-equilibrium system, time reversal invariance broken, and so on and so forth. So, but I have no clue what I'm going to work on at IBM, right? So here comes Vicsek. Vicsek was, again, another anecdotal. Vicsek, at that time, Laszlo Barabasi, the network guy, guru, he was a postdoc at IBM, right? And Vicsek was his master thesis advisor at that time, Romania. So actually he joined IBM and said, oh, why Vicsek visiting East Coast, why don't we invite him to give a talk? So he gave a talk, 94, in November. I still remember, early November, he gave a talk at IBM. And he talked about his Vicsek model, right? And here are the three ingredients what I just told you about of flocking. First, it moves. Not only it moves, the velocity, the amplitude of the velocity is constant. It always moves, right? The direction is second equation, but it always moves. And at any given time, it always moves with a constant speed. And how do you decide the direction? You decide the direction by drawing a circle of radius r, and you look within the radius r. See, you have no anisotropy, no asymmetry, no discrimination. Anybody within that circle. You measure its direction, you average it, right? Well, what is the third ingredient? Noise, right? So if you average it and you perfectly average it, that's this perfect decision. But you average and you add a little noise. And the noise is basically measured by the trends. In this case, I just have a uniform noise between minus eta over 2, eta 2. So the region of noise angle is at eta, because I don't want to put Gaussian noise. I want to have a bounded noise, right? And the magnitude of the velocity is v. That's it. That's the model. Very simple. So that means even though physicists are not the first to model flocking system, we physicists have the simplest model, minimum model. That's always the case, right? That's always the case. So keep that in mind. Yeah. Well, if you assume some continuity, then it does, right? So also you can include yourself within that measurement, right? So that, yeah. Okay, so that's it. So everybody can do, say yes. Say again? Oh, that's a parameter in the model. So that has to be bigger than the average distance between two voids, and which can be calculated by the system size and the number of voids in the system, right? That's a parameter, that's true. So how many parameters do you have? You have R, you have number of voids in the system size, which is the density, give you the density, and you have noise strength, right? So you can change either the density relative to R or the noise strength, either way. What he did was he just put that in the computer. He simulated the system. And he found that when eta increases, so everything kept fixed. I forgot the number, the R he chose here. Everything fixed, you just change eta, the noise strength. On the left at low noise, what he found is that, everything seems to be aligned. How do you measure the alignment or the flocking speed? Just simply you come up with some order parameter of the system, which is basically the average velocity, the magnitude of average velocity divided by average, and right, divided by v, which is the magnitude of the individual flock velocity. Right? If it's perfectly aligned, you get order parameter be 1, right? If it's not aligned at all, if it's random, then you get 0 up to 1 over square root of n correction. Right? So that's finite size. So he did it for n equals 40 to 10,000. As you see, this finite size effect diminishes as n becomes bigger. And when n goes to interpolate, n goes to infinity, he sees from his simulation a transition from ordered to disordered as you increase noise. The same thing would happen if you, instead of increasing noise, you decrease the density, right? Okay. So that's his observation. So he will talk about this. Everybody's very happy in the audience. And then, oh, so let me not talk about this other model. Let me save it for, yes. Yeah, there's no free energy, just order parameter going from non-zero to 0. And if you later on, I tell you it's about a symmetry breaking. I mean, you have ordered state, and the ordered state actually in 2 dimensions has to correspond to a symmetry breaking. So in that sense, it's very similar to equilibrium SAMAC, and that's actually a very important point to keep in mind, because in that at the overall sense of defining the phase transition is very similar, but underlying the mechanism is very different in such a way that even in 2 dimensions you have long range order. Yeah. Okay, so I will skip this. So AIM is another simple model for flocking, but on a lattice. So what I talk about Vicsek model is off lattice, right? So it's actually we think it's similar to XY model, equilibrium model, but XY model is on a lattice. So that's not quite the same as XY model in terms of alignment. Here there's an AIM model called an Active Ising Model, which I will tell you more about on Friday. Okay, so because of time, I don't want to go too much into, but I will talk about this in the context of how I use this model to show detail balance is actually broken at the microscopic level. Yes. Yeah, so the steady state, yeah, this is all, these order parameters are all measured in the steady state. How do you know it's a steady state? You just, in your simulation, you just look at whether the time, it actually changes with time, but initially it goes from 0 and up to some level, and then it just fluctuates. Yeah, this is true. This is all what I would call non-equilibrium steady state, right? It is a steady state because it doesn't change. This property, VA, doesn't change with time. But this is not your equilibrium steady state. So going back to your question there, and actually that's becoming very important. Okay, I will not talk about this. Okay, but wait, there's a big problem. That's where Vicek's talk went, very in a different direction. His mood just saddened because they sent the paper at that time to PRL, and the referee came back saying, this cannot be true. Your system is not large enough. You have made some mistake. Your model is not, anyway, because of Mermin-Wignath theorem. So what is Mermin-Wignath theorem? Mermin-Wignath theorem is that continuous symmetry cannot be spontaneously broken at finite temperature in systems with sufficiently short range interaction in dimension less or equal than 2. So first of all, continuous symmetry, what does it mean? It means that the orientation, the speed it has O2 symmetry, right? At least in the underlying model itself. But if you say it's flocking in the same direction, the symmetry is broken, right? You have to pick a particular direction to flock into. And according to Mermin-Wignath, well, if you literally understand it from this theorem itself, just literally that cannot happen because there's a soft mode, goldstone mode, that will destroy you with any finite temperature. The rough calculation basically amounts to saying, okay, suppose you do have that symmetry broken state, you can look at the fluctuation around it and evaluate, calculate how big that fluctuation might be with a given temperature, T fluctuation. Right? And you can, the rough calculation, which I will go through, is that actually goes like T integral over the phase space. In case this is a K space, divided by K squared. Why K squared? Because the energy costs of deviating away from each other. So this is arrangement. This is a goldstone mode. The goldstone mode is a mode that you are locally pointing to a direction very close to each other. So if you're next to each other, you are close to each other with an angle that is inversely, that is 1 over K, basically. And there's a cost for that because if you write down G functional for this, because you have not perfectly aligned, the cost go like 1 over K squared. And well, all right. Yeah, the angle is 1 over K. A large K. No, small K, sorry, small K. A small K is large wavelengths fluctuation, and within two sides, the angle difference goes like A over A means the distance between the nearest neighbor divided by lambda, right? So therefore, the angle goes like K, and if it's cosine, then it's the correction is K squared. That's where the energy cost comes from. And if you integrate over the phase space, this mode, even though it costs a little bit of energy depending on proportion to K squared, the entropic gain, right? With a finite K, you gain a lot of entropy. Entropic gain overwhelms the energy cost. So as a result, your fluctuation actually can go logarithmically with the system size, which means that of course, that just basically means the symmetry broken state is unstable. Right? I'll go into more details with this. But basically that's what, in 2D, that's what this goldstone mode and Mermin-Wignath theorem is telling you. Therefore, he's not happy, no long range order, and his paper was rejected. Yes. Well, look, what is this? Temperature, right? Temperature times delta S, that's entropic gain. This is basically the phase space area, the volume in the phase space, right? With a K, with this kind of a wavelength. Well, I'll get to that a little bit more, but this is just a hand-waving argument to tell you the reason is that you can make a little bit of you can deviate from your ground state, and of course your cost of energy will be less likely on one hand. But if the deviation from it, you have many ways to deviate from it, then that's the entropic gain or entropic cost, whatever you want to call it. The entropic gain will actually dominate over the cost. So as a result, your free energy is still going to be preferring the disordered phase. Right.
Are you going to tell us if walking is actually
Oh, of course. That's the set. Yeah, that's a equilibrium result. Yeah. 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 Okay. So yeah. So for the rest of today and tomorrow, what I'm going to tell you is the following: that okay, so how do you solve this problem? So that got us intrigued, right? So I tell you that I'm going to tell you something you don't find in the paper, is that we were in the audience for the talk, probably in room 2043, and we were really intrigued, both John and I. So we jumped up, and almost by next day we had a model, basically what people call the Toner 2 model, a Toner 2 equation. By the next day, and before he left, we actually told him that we may have found a answer for his problem. Okay, so in the rest of today and tomorrow, hopefully I can tell you that, or show you that the critical dimension for the linear analysis or equilibrium analysis actually equals 4, below which you have to consider the nonlinear non-equilibrium effect. And using how do you do that? You're using RG, and using RG, you find indeed the cost is actually more. So remember, this is actually K actually small, right? So with a smaller exponent, it's actually larger. So this is actually will cost you more to misalign. So anyway, but that's basically I'm going to tell you in the rest 1.5 lecture, not quite 1.5. Okay, so that's basically the history. And again, this is something. Notice that the paper was received. The Vicsek paper was the Vicsek paper was received 25th April 94, and he gave the talk at August 94. November 94. That was when the paper was rejected, and it was then published right after a year and 4 months. Why? Because we're sending out, I think, we're sending out paper in June next year, and then the 2 paper was published not too far apart, about 4 months apart. Yeah, NPR. So that to me is a very happy ending. Oh, again, look, this is a plagiarism, right? So we did write to him. Flocks, herds, and the school, a quantitative theory of flocking. What did he say? Forgot. Yeah, a distributed behavior model, right? So this is a difference. Good point. I should check. Oh yeah, of course. We had the sort of the rough model right away, and remember the paper was published the next year in August. Yes, it's a long. It was no, they resubmitted. I mean, because of our work and using that as evidence, right? So which is, yeah. So I can find out the history, but I think, and both of us agree that's the case. That's basically that's a pretty happy. This is what I say, right? This is a happy ending. Happy ending for flocking theory, but it's also even happier because it's a new beginning. I think people cited this as work as sort of a starting of the active matter. We didn't know anything about active matter or definition of what is active matter. We were just worried about whether you can have long range order in 2 dimensions at all, right? So that was. Right. Okay. Okay, so the next half an hour, I don't think I'm going to use the board because it's I have enough slides to go this because it's all right. Okay. So again, let's go back to be serious. Serious. Hydrodynamic theory about back to the topic, right? So you're going to see some equations now. I'm pretty sure you're looking forward to see equations. So what is hydrodynamics theory? It's basically a coarse-grained continuum theory, right? It's nothing. There's no misdefine this. This is just basically continuum. You want to look at the system instead of discrete and microscopic model. You want to look at the coarse-grained continuum model, right? And what do I mean by that is that you want to look at the effective model at a large scale, both in space and in time. So you're interested only in scale that much larger. For example, in the flocking Vicsek's model, much larger the interaction length scale are, and much larger than the interspacing between two birds, right? And you're also only interested in large time scale, where t is much bigger than the speed, the time it takes for you to actually travel from one center of the interaction radius to the edge, right? That's the typical time, small microscopic time scale. But okay, so that's all good. And so how do you do that? Actually, as John would say, that makes problems so much easier. Why? You don't care about microscopic, right? You only care about is the dominant term, relevant terms. You just write down all the relevant terms that are consistent with symmetry, conservation law of the problem. For example, in the case of hydrodynamics for fluid, well, first of all, the relevant hydrodynamic variables are the density and for compressible fluid and the velocity field, right? What are the symmetry? You have rotation symmetry, unless you break it somehow by, yeah. And you have space and time translation invariant. It's translation invariant. I didn't say time reversal invariant. Translation invariant and Galilean invariance in that case, right? Moving the moving frame, the equation should look the same. And of course, conservation law, you have conservation of particle number, moment, and energy. So based on these, you can write down the equation, maybe not, because there are many, many terms that are consistent with conservation law and the symmetry. Which one do you pick? So here's hydrodynamic limit comes in, right? What do you pick? You pick the lowest derivative term that consistent with the symmetry. For example, if you have both, second derivative in t, and I'm not saying you should put this in because it obviously breaks the reversal symmetry. Right? But just in other system, if you can imagine, you can put in both second derivative and the first derivative. You should just keep the first derivative. Second derivative is irrelevant at a long time scale, right? And if definitely in this case, for example, here for the diffusion for the viscosity term, you have the second derivative, right? You have a Laplace term, and you could have the force, which is totally happy, consistent with symmetry and all that stuff. But you don't put it in because your hydrodynamic limit. This is the smaller term. So that's it. That's basically why John was happy to say, well, okay, this makes the problem easier. Let's do that. And then we actually basically, the same idea basically applies to many other systems, hydrodynamics theory of other systems as well. So this is nothing new here. We just did that. So again, remember there's three things to incorporate into the model, right? First, it moves and transport material, including itself, right? So you have to add in the sort of advective term, right? So this is actually, so that's a nonlinear term, but based on power counting in terms of hydrodynamic limit, you cannot discount it because you don't know how V scale with length or time, right? This one, I'm not sure I would call it alignment, but this comes from the argument. This is a term if you're familiar with ferromagnetism and 5-4 theory. This is a 5-4 theory basically says, well, you have the possibility of break the symmetry so that you actually have a finite value for the average spin or average velocity, right? When alpha is bigger than 0. It originated from the, for example, the Ising model, the ferromagnetic coupling, or Heisenberg model, XY model, ferromagnetic coupling. So that's why I said, well, sort of alignment, a little subtle, but this is a coarse grained theory. And there's a noise. There's noise here. We're putting right noise in space. What is this term? Well, this is a pressure term because it's a hydrodynamic system, and also the density does fluctuate, right? So we put in a pressure term, and because density fluctuation, we also have to say, well, there's a conservation of total number of active particles in the system. So we write down the conservation law for the total number of particles, right? And then you have to have a constitutive equation relating the pressure and the density, right? So we just did nothing but Taylor expansion around the mean density, rho 0. You have sigma 1, even sigma doesn't matter. Sigma 1, 2, 3, 4. Right? So just very general. Yes. Yeah. Phenomenological. These are terms allowed by the symmetry, and phenomenological in the sense that we want a transition from alpha disorder, which corresponds to alpha less than 0, to alpha bigger than 0, where V has a minimum. Just based on this part, if you write this as a derivative of a potential, this will have a minimum. Alpha bigger than 0. We will see in the next slide, we have a Mexican hat potential, right? And that's where the symmetry breaking will come in, and all the analogy to equilibrium stat-mac will come in, and then claiming that if you forget about nonlinear term, that will destroy your long-range order in 2 dimensions. Well, I think this definitely is a parameter. The magnitude of the alpha over beta, square root of alpha beta, give you the magnitude of the velocity, right? And well, I should put a D here. Diffusion constant. I missed the D here. My mistake. My bad. Okay. Diffusion constant. And then the sigma. So we usually keep only the sigma 1 and sigma 2. Sigma 1 is the sound speed. I'll come to that maybe tomorrow. And sigma 2 is some parameter that's very much the same as the lambda, the nonlinear coupling constant. Yeah. Yeah, so that you'll come to next slide. So yes, let's go there. Okay, here. Yeah, there's a question. Yeah. Which term? This term. Yeah, but if I move, I carry myself, and I also the velocity is the velocity itself is something that you carry, right? If I have a velocity, I move, that velocity is being carried to the next. It's being carried along. Yeah. So I'm not talking about this is about the velocity field of the flock of the boids. I have nothing to do with this is not the speed of the fluid, right? Yeah. Again, I mean you can argue about the physical meaning of this, but the bottom line is remember, close your eyes and just write down all the terms that are consistent with symmetry, conservation law, and the lowest order in the hydrodynamic limit, and that's one of the terms. And you will see that what I give you about advection is just not quite right, because if it's really advection, advection, lambda should be 1, but it's not. Yes. Yeah. Yeah. So again, don't think about some really deriving it from microscopic. Think about symmetry, think about conservation law, think about lowest order term.
I mean, I guess the assumption is alpha and beta are independent of this.
Oh, that's a good point. For now, yes, but if you really derive from microscopic, alpha beta could very well depend on, because remember, when you change the density, it goes through a transition, which means that if the transition point corresponds to changing alpha, then that means alpha depends on rho, which I think people have shown that. Yeah. How much time do you have? Yeah. It's not strict Galilean, but it doesn't come from Galilean invariance. Okay, so all I'm saying is that, look, maybe in the microscopic model, you do put in this one. But as you know, when you go to higher, larger scale, if you lambda start with 1, lambda get rescaled. Why? Because this term breaks Galilean invariance. It has a preferred speed, right? Galilean invariance is invariant for any speed that you move. If you put in v minus v0 here, it's not symmetric here. So even if you put lambda 1 equals 1 at some microscopic scale, when you go to larger scale, lambda will deviate from 1. Yes. Oh, what? So you say again? Oh, it's not incompressible here. Yeah, so it's compressible. So there's a variation of density, and in simulation you see variation of density, and that causes because you have a density variation, the alignment, and so on. Again, it's very hard to think about these terms in microscopic level, but these are allowed by symmetry, right? So you're allowed to have a term that's a gradient. So this is a vector. This is a vector. So rotation symmetry is okay. And this has to be a scalar. And the scalar can depend on v squared and rho, right? Right now, we forget about the v squared part because that's a high order term you can show. So only dependence for the p is dependent on rho. So it shouldn't be considered as a pressure in the sense of the hydrodynamics of fluids, but it's a pressure term coming from the density fluctuation and affect the change of velocity of the flux. Yes? Right. Oh, did I write it wrong? Yes, sorry, I was wrong. Sorry, thank you. That was wrong. Yeah, so this is only incompressible fluid, right? Sorry, that you're right. Yeah, so I think you caught it first. Okay. Let's quickly go here. So this is the situation, right? So once you presented a model like this, it's hairy, right? What do we do with it? The first thing you do is you look for the simplest solution possible. So what is the simplest solution? Well, of course, a spatially homogeneous solution, right? You don't look at any patterns. You say, okay, rho is constant, rho equal rho 0 everywhere, and v is a constant everywhere, right? So immediately you drop all the horrible derivative term, right? All this term goes away, boom, right? Boom, boom, right? Forget about the noise for the moment. You just left with this term and this term, right? They say, what is the v? What's the spatially homogeneous solution? Okay, that depends on alpha. Beta is always positive, right? Depends on alpha. When alpha is less than 0, you get a solution that v equals 0 here, and it's stable. The only thing I draw this as a potential, right? But the only thing you need to know, because it's a dynamical system, this picture is actually harmful in some sense. It's only valid in the equilibrium system. But what you need to know is that this point is stable fixed point. That if you little bit perturbation, you go back to here. That's what this landscape is telling you. Whereas here, again, the same thing, that, okay, when alpha bigger than 0, you know that then the solution can have a finite magnitude equals alpha over beta, but there are many, many of them because it's 2-dimensional. So everywhere in the bottom of the potential here is a solution. So which one do you pick? Well, you randomly pick one. That's the spontaneous symmetry breaking. So if my solution is here, I'm moving north. So that's a good solution, right? If you neglect all the spatial dependence, you forget about noise, that's a solution. Nobody can argue with you. So there comes the next point, is that once you have a spontaneous broken solution for the system, spatially homogeneous, then you have to ask the next question. Is it stable? Right? We just told you that on the spatially homogeneous perturbation, I'm not sure. Why I'm not sure? If you move in this direction, it is stable, right? The parallel direction. So this is what I'm trying to tell you, that the perturbation, okay, here. The perturbation up there, so I'm not gonna draw on the board, has 2 directions. You can perturb, right? You can perturb around the parallel direction, along the direction of symmetry breaking direction. That's around this direction. And you can see immediately that it's actually stable. And you can show it, you can derive it. You can calculate the d parallel dt, dv parallel dt, and you get negative coefficient times v parallel. This is high order truth, look at it, right? So which means that actually, this is actually, it's a stable, actually quite stable, right? There's a negative coefficient in the time group. So this is a stable direction. However, if you perturb around this direction, tangential direction, perpendicular direction, it's all flat. So we don't know, right? It's what people in condensed matter physics or in high energy physics call is massless. There's no mass. So this is also a soft mode. So this is a Goldstone mode, right? So this Goldstone mode is correspond to somewhere that doesn't cost you any energy. If you think about this energy landscape, it doesn't cost you any energy to go this direction. It's soft. So any perturbation can excite that mode. The question is, how much does it excite this mode? Is it enough for you to destroy this steady state, that symmetry broken state? Okay, so that's the question. So the slow Goldstone mode is potentially dangerous. So you go in there, so the equation, you plug in the perturbation. So you plug in the V equal V0 plus, now you only keep the red perturbation, the perpendicular perturbation. And you plug it in, and you write down to the leading order term. And you can say, well, the second order term, the nonlinear in V perp, including V perp times delta rho, you can first ignore it. Let's do the linear stability analysis. Okay. And in the co-free, if you drop those terms, if you do linear stability analysis by dropping the nonlinear term, you obtain the black equation, right? Just dropping the high order term. And that is a linear equation. You can solve it. Remember, this perturbation is spatial temporally varying, right? So you have to do a little bit harder work. You have to go to Fourier space. But if you go to Fourier space, it's still a linear equation with 2 variable, V perp, which is in the 2-dimension, it's actually only one direction, right? In the perpendicular direction, it's only one direction. So V perp is a scalar. Delta rho is also a scalar. And you can solve it. You can say, okay, now I don't need to have this vector here. You can solve it. It corresponds to this. This is a noise driving force, right? This is an inhomogeneous term. Divide by times the Green's function, basically, if you wish, in the K space, right? And you can recognize it's actually very interesting because the compressible fluid the zero mode, the pole is actually at omega equals CK perp. So this is a sound mode. We will talk about tomorrow. But anyway, you get this formula, and you know the correlation of, you know the spectrum of the noise. You actually compute the variance of the fluctuation. You see how big it is, right? Which, right. It's dropped out. Oh.
He's expanding.
Yeah, expanding around the square root of alpha or beta. So here, I set it to be 1. Okay. I said alpha, square root of alpha or beta equals 1. Okay. Okay. So if you want to do a homework, this is a perfect homework to do. This is nothing, to it, right? You can solve it. And given this, you know the fluctuation, the strength of the noise. You know how this depends on the noise and the Green's function. And you can compute for 2-dimensional system. You actually can compute the variance, right? The equal time variance of the fluctuation, V perp, and that comes on this formula. You can first integrate out the omega and write the pole. So the spread is dk to the fourth. And if you integrate out the omega first, then you get the dk term integrate over k, and that basically becomes the formula I just gave you before by hand waving argument. This is actually computed from the linearized hydrodynamic equation, right? And you get this delta over d log L over R, right? So unless delta equals 0, unless you have no noise, this term, as you become larger and larger L, this can always become order 1, right? So your order will be unstable. Your order state will be unstable. It doesn't diverge, of course. When you get on order 1, you have to consider a higher order term, and then that. So, but anyway, the fact is that is not constrained. This term is not bounded. It's actually keep increasing. Temporally, you can also calculate at a fixed position, how does it change over time, right? Actually change logarithmically with time. So also again, it's increasing, unbounded at the linear level. So the symmetry broken order stays unstable against noise in 2D. I have not invoked anything about entropy or energy cost. It's a non-equilibrium model. At the linear level, it actually can be mapped onto an equilibrium model. I don't use that, right? I use time-dependent, linearized equation. I solve it, and I get Mermin-Wigner theorem. Of course, this is much more general than I was just showing you here. So again, this is Wikipedia. The authority says this, right? So I mean, you already see this, right? So at a finite temperature, that means that at any finite noise level, you're gonna destroy your linearized equation. The spontaneous broken state is gonna be destroyed. Intuitively, this means that the long-range fluctuation can be created with little energy cost, and since they increase entropy, they are favored. So that's what, in the equilibrium sense, that's what people usually argue, that a small, like a spin wave fluctuation with a long wavelength costs you very little energy, but the phase space it created, right, is much larger. It dominates over the energy cost. So therefore, this fluctuation favors. But you see, even long wavelengths, after you go one wavelength, the spins are opposite to each other, not correlated anymore. That destroys the long range order. So yeah. So you have seen all this in this little simple derivation I gave you, but that has nothing to do with sort of equilibrium picture. It just, you can derive it. So what I'm saying is that all these sort of high-level concept, you actually can see it in a simplified model, or not in a specific model like we have but the concept is true, right? So you can then you can look at the Mermin-Wagner theorem and say, aha, now I understand the O2 symmetry. Why I have O2 symmetry? You need the spontaneous broken symmetry state. The order parameter in the original system has O2 symmetry. That means there's a soft mode, because if I move a little bit to the left, to the right, I change only a little bit, the cost, the restoring force is very weak, right? But if I have a lot of fluctuation to drive you away, then you're going to be driven away. The restoring force is actually not enough to restore the order. So that's the way to sort of understand it. And that mode is soft mode, is both Goldstone mode or so on. Okay, so just sort of a prelude for tomorrow is a possible way out of the Mermin-Wagner mess. We call it a mess because the disorder is a mess. So what could happen? So remember, the analogy that I used is that the entropy gain is the numerator, delta ddk, the phase space, right? And energy cost is in the denominator, dk squared, right? And the reason it diverges in the infrared limit, in large wavelength limit, is because, with small k, is d minus 2, right? 2 being the denominator. But this comes from sort of the diffusive term, right? In our equation, the linear diffusive term, d grad square v, right? What if the effective diffusive term is d to the k to some power of z, and z is less than 2, right? Which means that a smaller k is actually a little stiffer. It costs you a little bit more. The restoring is a little stronger. And in that case, if indeed, if you have that with z less than 2, then the velocity variance will decay as L d to minus 2 will decay to 0 as L goes to infinity. Or there's a constant term in front, will actually remain constant, remain small proportion to the delta. Right? It will not diverge, right? So long range order will actually survive. So we are hoping that, remember the term we neglected, the v dot grad v term, lambda 1 times v dot grad v term, it's some kind of a transport term, right? Move things around. Diffusion also moves things around, rearrange things, the direction. Maybe the hope is that nonlinear effect will lead to an effective a diffusive term that has a power less than 2. And in that case, then long-range order will be restored. And for us to see that tomorrow, we'll talk about this nonlinear effect, critical dimension, RG. Maybe you should talk about it. And scaling. Okay, that's it.
Any other questions?
Yeah, I think has some connection. Yeah. I think it's basically about the nonlinear effect, right? You have the convective term in turbulence, which is very important in the inertial range, and that will create something that actually will be stronger in terms of transport than diffusion. That's what. No. That's that. No. I've been trying to be careful, but also. No, if beta is negative, then you keep growing. That you have to damp it with some high order, even higher order term, right? No, but it could become first order transition, which some people think they have seen first. So you're right. So if both alpha beta equal positive, become alpha positive, beta negative, then it keep growing, but it has to be brought down. But when it brought down, it will be brought down by a high order term. As a result, the transition will not be a continuous transition to, the order parameter will have could have a finite jump. And that's first order transition. And that is not what we're considering here. No, ultraviolet, we have a finite cutoff, right? Yeah, we don't, The infrared is what long wavelengths is what we worried about here, right? Good question. Right now here is definitely short range because the next nearest neighbor. But technically, that's what Mermin Regner was actually being careful here, is that long range fluctuation can be, okay, so he says, sufficiently short range interaction, right? That's very tricky. What it means is that you could go as 1 over R to some power, but that power has to be large enough to be short range, right? No, in all I'm talking about is strictly sort of orthodox short range. It has a finite length, e to the minus R over capital R, right? It's not exponential, not power law at all. Demographic noise meaning? You mean color noise? Yeah, so the theorem depends on, it's assuming this the noise is white and thermal noise. Well, that has nothing to do with mean field. It,
this model basically white noise.
White thermal noise. Basically, thermal noise you write down as sort of white Gaussian noise. It's a good approximation, right? Yeah, it is sort of, yeah. So John later on worked on a version that is actually incompressible flocking model. And in the incompressible flocking model, he was able to map that into a KPZ equation. But you're right, it has a lot of similarity in terms of its nonlinearity in the order parameter V, but its first derivative, right? V dot grad V is first derivative, whereas KPZ equation is grad H squared, which is second derivative in space. But I think there's some transformation you can do that you can bring them together, at least in terms of order. They are the right same order. But of this particular model for the compressible case, no.
Friday, and they're going to drop off lumens, fresh lumens in your room. It's all along, but I stopped by the front desk today. Yeah, so am I. So